Hello everyone. In the previous class, we learned about Lebesgue measurable sets and Lebesgue measure. We knew that a subset E of a set R is Lebesgue measurable if for some set A, M star A is equal to M star of A intersection E plus M star A intersection E complement. Now today we'll construct a non-measurable set. Before that, we'll see some results. Two real numbers x and y in semi-closed, semi-open set 0, 1, we define the sum modulo 1 of x and y as x plus y if their sum is less than 1, and if their sum is greater than or equal to 1, then it is x plus y minus 1. So that in any of the case, the sum of x and y will always be present in the half closed, half open interval 0, 1, and it is denoted by x sum modulo 1 y with this symbol. So if x and y are coming from this, then obviously that sum modulo belongs to this. Now similarly, we'll define the translate modulo 1 of E to be the set consisting of all elements of the form Z, where Z is the sum modulo 1 of x and y for some x in the set E. Now we'll come for a lemma. Suppose E is subset of this and it is Lebesgue measurable set. Then for each y coming from half closed, half open interval 0, 1, the translate modulo 1 of E, that is E translate modulo y, is a Lebesgue measurable set, and further the measure of this translate modulo of E is same as measure of E. Let's prove this one. Let us construct two sets E1 and E2. E1 is E intersection half closed, half open interval 0, 1 minus y, and E2 is E intersection half closed, half open interval 1 minus y to 1. So these two sets are disjoint in fact, and further their union is E, and so measure of E is measure of E1 plus measure of E2, because E is the union of E1 and E2, and these two are disjoint. By the earlier results, measure of E will be equal to measure of E1 plus measure of E2. Now the translate modulo of E1 is E1 plus y itself, because here any element which belongs to E1 is greater than or equal to 0 and less than 1 minus y, so that x plus y will be always less than 1. Therefore, the translate modulo of this E1 plus y is same as E1 plus y, and so this translate modulo of E1 is Lebesgue measurable, because E1 is Lebesgue measurable, and the measure of E1 translate modulo of E1 is same as measure of the E1 plus y. But we know that if you add finite terms to any set, measure will not change. So measure of this will be same as measure of E1, since M is translation invariant. And also the translate modulo of E2 is, because we know that if any x belongs to E2 means x belongs to this. So you, in this case, your x will be greater than or equal to 1 minus y. So your x plus y will be greater than or equal to 1. So in that case, your E2 translate modulo of E2 will be E2 plus y minus 1. Because of this reason, if x plus y is greater than or equal to 1, and it has to be expressed by -1 because of that reason. And so E2 translate modulo of E2 is also Lebesgue measurable because it is equal to E2 plus some finite term. And further, the measure of this is measure of this. Since M is translation invariant, the measure will be one and the same. But what is your translate modulo of E? The translate modulo of E is translate modulo of E1 union translate modulo of E2. And further, these two are disjoint Lebesgue measurable sets as we proved earlier. So measure of this will be equal to measure of this plus measure of this by earlier results. But M is translation invariant, and we have proved measure of this is measure of E1, measure of this is measure of E2, which is nothing but measure of E. So this completes the proof. Now we'll construct a non-measurable set. Let us say x and y are equivalent provided x minus y is a rational number. Then this is an equivalence relation. You can verify it is satisfying reflexive, symmetry and transitive conditions. And further, it partitions this into equivalence classes. Let P be the set which contains exactly one element from each equivalence classes. So your P is a set which contains the elements from this in such a way that one element should come from one equivalence class. Then we'll show that this P is non-measurable set. Let us assume a contradiction to this, that P is Lebesgue measurable. Now let Ri be the set of rational numbers in this with R not equal to initial value 0. And now we'll define Pi is translate modulo of this P translate modulo Ri. Then this Pi is a sequence of disjoint sets, and in fact the union of Pi's will be same as the half closed half open interval 0, 1. Why? We'll prove it. For each I, you should note that your Ri comes from this and P is also containing elements from this only. Therefore, your Pi must be an element in this only. So it has to be a set of the subset of this. So for each I, if this is present in this, then obviously its union is also present in this. So we'll prove the other way so that these two sets will be equal. We know that two sets are equal to each other provided one is subset of another. We have proved one set is subset of another. Now we'll similarly prove the other way. Suppose X is present in this half closed half open interval. We knew that all the values of closed interval 0, 1, the half closed half open interval 0, 1 are present in some equivalence classes. Therefore X is also present in some equivalence class. And so it is an equivalent element in P because it contains exactly one element from each equivalence class. So that means X differs from an element in P by a rational number Ri. That is, X belongs to Pi. X belongs to Pi, but X is an element from this. Therefore, it belongs to this union. So we have proved both of them. Hence, this result is true. That is, union of Pi is nothing but half closed half open interval 0, 1. And further, we should note that we have assumed P is Lebesgue measurable set. Since M is translation invariant, this measure is same. And so, measure of half closed half open interval must be equal to measure of union of this. Since these are disjoint, we add a result which says if these are disjoint, then measure of union of pi is summation pi. So by that result, summation I from 0 to infinity mpi is equal to this. But since this is translate invariant, therefore measure of pi is same as measure of p. But see, the measure of left hand side is 1, whereas the measure of this is either 0 or infinity, depending on measure of p is 0 or positive. But this is impossible, hence our assumption is wrong. That means p is a non-measurable set. I'd given some exercise. You write these as assignment and submit later. Thank you.